No, they'll explain it to you. I have an idea of someone that might.
Oh.
I think, Laura, raise your hand.
Why did my hair stand on end?
I think, well, why do your hair stand up?
Yeah.
Because
remember what we went through. The electric field, which is a force. The electric field is negative. It's a negative charge. But it could do the same thing with a positive charge. My body, entire body gets charged. As she put it out with, what is it? Yeah. It went right through my hand, right? So my entire body gets charged with an excess of electrons. Those electrons would like to get off my body. And the ones on your hair would like to get as far as away from the charge as they can. And each hair gets, my gray hair is the best. There's no color. Which is why I was going to pick this girl next, but she says no. How long is your hair? All right, quiet down. Quiet down. There's a reason I pick it first. Why did I pick this up? Anybody have an idea? His hair is long enough to demonstrate what I'm trying to demonstrate. There's people here with longer hair. But why did I pick him?
He's well dressed.
Touche. Touche. Anybody know what touche means? No, this young lady with much longer hair. Why did I not pick her? One of the two forces, don't go away. One of the two forces that will be acting on your hair when you get fully charged.
Gravity.
You gotta speak up. I want you to project.
Gravity.
Whoever gets on there will have electrons in their body. But why not? Why won't your hair stand on end? The two forces that are acting on your hair are gravity and the electromagnetic force that's on the charge. So your hair is very long. That means it's going to get further away from the charge. That means the force of gravity will act more on your hair than on this young man's hair. Unless you haven't put anything on your hair this morning. Good. You're a perfect candidate. Get up on the block. I want you to loudly, quiet. I want you to loudly describe what's going on in your mouth. By the way, keep your mouth closed. I see you have braces. I will explain why I made that statement. The braces are metal. And they're going to want to discharge from the... What do you feel? Nothing. Now, as you... What do you feel? I want you to describe your feelings. He says he's got a tingling. You will start to feel a tingling. Your other hand, brush your hair. Come on, brush it up. Yeah. That's pretty good. Yeah, You feel what? No, no. Okay. Justin, take your hand off. Take your hand off. Did you feel anything? Just a little bit. Why isn't the hair still standing up? He's not grounded. You're beginning to get it. He's not grounded. He's still charged. Good job. Now he's grounded, rooming, and as you can see, he's charged beginning to ground. Thank you very much. Give him a hand. All right. I want to leave a little bit of time for questions. And if you don't ask any questions, I may ask. Anybody got any questions? What's the difference? What's the difference between the charge that we get on the sphere and the electricity that we get from the plug? Can anybody tell me that? What kind of electricity do we have coming out of where I'm plugged in? Plugged in simply to run the motor. No difference?
Current electricity rather than static?
Well, when I discharge that, it's electricity is flowing. By the way, just to give you a number that's worth storing in your head, current is measured in coulombs per second going past the given point. Has nothing to do with the question I have raised, but that's how current in amperes. 1 ampere is 1 coulomb per second going past the given point. That's 1 ampere. When you run this machine, that's about a 1/20th horsepower motor they've got in there. Yeah, so you're running about a 1/10 of an ampere, 0.1 amperes. So that does not draw much power. But let me just show you one other demonstration. Now we have to use our ears very carefully. All right, we get this right. So that we've got a pretty good spark. Now I want you to listen carefully to the motor. There's a little motor there that's driving the belt. Listen carefully. What did the motor do?
It went faster.
What?
It went faster
When did it go faster?
when you got closer.
You're absolutely right. The motor speeds up. Why?
Because you're taking away the electrons that want to make more, so it's equal.
But then when I take it away, it wants to get recharged, right? But it slows down when I short it. What does that mean when it's not short? I'm doing more what when it's carrying a charge up the belt? Did we study any general science? Where are the teachers? You get nothing for nothing in this world. You have to do work in order to carry a single electron from the ground plane up the belt and force it past the charge that's already on the belt. You must do work. When I do work, and of course I'm carrying more than 1 electron at a time, when I'm carrying a whole bunch of electrons up the belt, they have to get past this field. There's no way we can demonstrate that the field exists down here because it gets a little bit irregular around that hole that's in that allows you to work above you. But you have to get past the field. All the way out here, we know we've still got a field, we still get a spark. And so to get past that field and get up to where it can get to this, inside the sphere, where it can be carried to the outside, I have to do work. So the motor recognizes. You have a teacher have a question?
Sure. So am I hearing you say that when the sparks come off more quickly, it's easier for the motor to get electricity up to the ball, so it works less? And when the sparks come off more slowly, it's harder and it works more?
Yeah, it has to work more to get past the fully charged sphere than when I discharge the sphere. I must do work on the electron in order to get it inside the sphere. Yes. Okay, we're at this time.
We keep our clocks on the late side, and that way people get here on time.
Okay, any questions? All right, I'm going to show you one more thing. If we don't have questions. If you don't have the ambition, all right, we get the charge back. Now, which way? This is a wall of aluminum foil tied onto a string, which the string is attached to a glass fishing rod. I use that. I never throw anything out, as my son will testify. Now, when I get this near the sphere, what will happen to it? Which way will it go? It'll get pushed away? Maybe, well, let's see. Let's find out. You know, this thing is one of the experiments. Find out. Let's see what happens. Oh. Did you see what happened? What? I bring this back out to ground contentions. I bring it close. What happened? What happened? Did anybody see what happened? Come on, let's see. Speak up.
It went close to the sphere.
It got attracted because a zero charge, as far as that sphere is concerned, is a positive charge. So unlike charges attract, let's do it one more time. You see how fast that works? As soon as the electrons get on here, it now has a similar charge with the sphere, and it gets repelled. So now I can get this thing go back and forth. And again, we see the belt speeds up. Now, at home it takes a little time and effort to build an anti-grav generator. If you've got any skill on the part of your fathers or uncles or whoever, you can build one quite easily, but you can build this yourself. And it's called, I love to write these things down. And of course, I see you're all going to take notes. This is called an electrophoresis. If you have a computer, which I'm sure every one of you do, I was born and raised in Greenpoint, Brooklyn, in the tenements of Brooklyn. And for us to say we all have a computer would be unheard of. Especially at the time I grew up, there were no computers. But I'm sure every one of you sitting here has access to a computer. Type in that word. I don't see any notes here, so I assume your teachers will repeat it for you. Type in electrophoresis. That's the correct pronunciation. And an electrophoresis allows you You need